All right, folks. So in this video, we'll look at another application to first order differential equations, and it deals with what's called Newton's law of cooling. Okay, so we're going to look at how objects are they cool with respect to time, and then we'll look at some examples, right? So let's get started. Oh God. All right, so let's get started. So let's say I have a bowl of soup, nice bowl of soup that I just took out of a microwave. And so with the so there's going to be two quantities to consider, right? So we're going to look at the initial temperature of the bowl of soup. We'll call it T naught, right? So so we're going to have a function which describes the temperature of the soup with respect to time. So I'll label this capital T of T. So this represents the temperature of, let's say, an object with time T. Okay. And we're also going to have the surrounding temperature, as they call it, the ambient temperature. Okay. So A degrees, this represents the ambient temperature. So this could be room temperature or outdoor temperature or what have you. So it's the temperature of the surroundings of the bowl, right? Or the object. So what we want to look at is we want to look at a differential equation of capital T, right? So we want to look at the rate of change of the temperature of the object with respect to time, right? So, and also if a object cools, right? Well, so the ambient temperature is affecting the temperature of the bowl by cooling it, right? So so like with exponential equations, the rate of change of the population was directly proportional to the population itself, right? So in this case, we're going to apply that similar logic, right? So the rate of change of the temperature of the bowl will be directly proportional to the difference of the ambient temperature and the current temperature of the bowl of soup, right? So we're going to have a constant of proportionality K times A minus T. Okay, right? So, um, or A minus T, right? So, or maybe I should say T minus A. It should be T minus A, right? T minus A. The temperature decrease. That's what I meant. Okay, so from here, right, this is just saying, well, the rate of change of the temperature is directly proportional to the difference of the current temperature of the bowl minus the constant ambient temperature, right? So from here, we can use separation of variables to solve this equation, right? Separation of variables. Okay, and so we'll have, so on the left-hand side, we'll have d capital T over T minus A, and this equals to K times dt. Okay, then if we integrate both sides, right, take the antiderivative, what that is going to be is, so we'll have the natural log of T minus A, and this would equal to K times T plus a constant. Okay. So normally when temperature, okay, so as the bowl of soup is decreasing in temperature, will even out. So the temperature of the bowl equates to the temperature in of the ambient temperature, right? So this quantity will be just positive T minus A, and this will equal to I'll also say Ln of T minus A equals to K times T plus C, right? And so if I remove this here, and I'm going to label out the initial condition over here. So if we exponentiate both sides, right, we'll have T minus A equals to e to the KT times e to the C. So times a constant. So we make that a little bit clearer. So it'll be C times e to the KT. And so T of little t would equal to C times e to the KT plus A. A being the ambient temperature. Now, since you know that T at 0, the temperature at time 0 equals to T naught, right? T of 0, this would equal to C plus A equals T naught, which leads to saying that C is equal to T naught minus A. And so the particular solution of a differential equation that expresses Newton's law of cooling is T naught minus A times e to the KT plus A. That is the function for Newton's law of cooling. All right. So let's look at an example. A cup of hot coffee initially cooled at 95 degrees Celsius cools to 80 degrees Celsius in 5 minutes, right? While sitting in a room at room temperature of 21 degrees Celsius. Okay, so using Newton's law of cooling, determine when the temperature of the coffee will be a nice steaming hot 50 degrees Celsius. Okay, so pause the video and I want you to formulate a function, or I should say formulate a model that expresses this scenario. Okay. All right, so I assumed you worked on this example. So real quick, let's look at what the model for expressing this temperature of the hot coffee would look like. So by Newton's law of cooling, right? This is the function that we want, right? And we know that the temperature at time 0 is at 95 degrees, 95 degrees Celsius. The ambient temperature is at 21 degrees Celsius. Okay, so this function will be in degrees Celsius, right? And so this would equal to 95 minus 21 degrees Celsius times e to the KT plus 21 degrees Celsius, which is equal to 74 times e to the KT plus 21. And that's our function, right? Okay. All we need to solve for is this constant decay of proportionality, K. So we need to solve for K here, right? So, and what we're going to use is the fact that the coffee is at 80 degrees Celsius in 5 minutes. So, so little t is in minutes here in this case. So when it's at 5 minutes, we have 74 times e to the 5k plus 21 equals to 80 degrees Celsius. And from here, we're going to solve for k. So we'll have, so here, solve for k. So if we subtract both sides by 21, we'll have 74 times e to the 5k equals to 59 degrees. And if we divide both sides by 74, we'll have e to the 5k equals to 59 over 74. Then if we take the natural logarithm of both sides, we will have that 5 times k equals to the natural log of 59 over 74. Okay. And so, excuse me, so the decay rate will be ln of 59 over 74 over 5. Okay. And computed that ratio. So K is about minus 0.04531 approximately. And so we have our function T at capital T equals to 74 times e to the minus 0.04531 plus 21. Okay, so this is our function. And then to figure out the temperature, figure out the time when the temperature is at 50 degrees Celsius. What we do is we just solve for T. Solve for T here. So we'll have 74 times e to the minus 0.04531 T plus 21 equals to 50. Okay. And so we'll have 74 times this quantity. And that is equal to 50 minus 20, 30, 29 degrees. And so we'll have e to the minus, so this is T. 4, 5, 3, 1, T equals to 29 over 74. Excuse me. And we'll have negative 0.04531 T. If we take the natural log of both sides, we'll get that minus 0.04531 T is equal to ln of 29 over 74. And so T is approximately over so that's K. So about 20.676 minutes. So approximately about 21 minutes, right? So you'll get a temperature of 50 degrees Celsius in about 21 minutes. Okay. So that's Newton's law of cooling. And then just a little side problems for you to work with. So that's about it for first order differential equations. Okay. So now in the next set of videos, we'll be looking at second order differential equations. So order, remember, order means the highest derivative that occurs in an equation. So when I say second order differential equation, I'm saying there's a second derivative in the equation, right? So, so we'll look at second order ordinary differential equations. Ordinary, we have a single independent variable. right? So stay tuned for those sets of videos, but otherwise, thanks for watching and I'll see you next time.